Example 6. A 30-pound object extends S spring 6 inches. Compute the work done stretching an additional foot. So let's try to illustrate the question first. So we have a spring, and this spring is stretched 6 inches by adding a mass, which is 30 pounds. And that stretch is 6 inches. So that stretch by adding mass is called delta x. So delta x is stretch by adding mass. And our scenario is, what is the work done stretching an additional foot? So on top of 6 inches, we're going to extend the spring extra 1 foot. So it will be like this. This is our delta x, which is 6 inches, which is half a foot, 0.5 foot. And we are trying to extend the spring additional 1 foot. And here is our mass. So this is case 3, Hooke's law, or spring related questions. Here we need to find K. K is the spring constant, and K is found by m times g divided by delta x. M times g is the weight of the mass, weight of the object, times gravity if it is in metric system. If it is not in metric system, you can ignore the gravity. So mass divided by delta x is in our scenario. So our mass is 30 pounds, and our delta x, which is the stretch by adding mass, is 6 inches, which is half, 0.5 foot. So 30 divided by half, which is 60, is our K, which is spring constant. So we're going to set our integral from a to b, kx dx. And here our k is 60, so 60x dx. And our boundaries are from the first stretch to the wanted stretch. So from 1/2, which is 0.5 foot, an additional foot, if we add together, it will be 1.5 foot, which is 3/2. So this is 1/2 plus 1, so it is 3/2. So this is the work done from here to here. So this is our integral to calculate the work. And I'm going to leave it here because antiderivative of 60x is 60x squared divided by 2, calculated from 1/2 to 3/2. You can continue this, but our setup will be like that. Let's go to question number 7. If a mass of 15 kg stretches a 400 centimeter spring by 30 centimeter, how much work is required in stretching 100 centimeter beyond its natural length. Okay, let's try to illustrate the question. We have a spring and there is a mass which stretches the spring 30 centimeters. So 30 centimeters is our delta x already, which is half a meter. And our natural length is 400 centimeters, which is 4 meters. And we have a mass which is 15 kilograms here. And our scenario is how much work is required in stretching it 100 centimeter beyond its natural length. So this is the natural length here before adding any mass and any stretch. And we would like to stretch from here to extra 1 meter, which is 100 centimeter. So half a meter is already extended, so we're gonna extend another half a meter. So from here to here we need to extend 1 meter or 100 centimeter more. So our integral will be kx dx, and our k here is mg, which is the weight of the mass, which is 15 kilograms. Now we have to consider gravity because it's in kilogram. 9.8 divided by delta x, which is 0.5, and our k will be 15 times 9.8 divided by 0.5, which will be 294. So here our integral is 294 x dx. And our limits of integral is from the natural length is 0, here is 0, and we want to extend it 1 meter. So 0 to 1. So this is our integral setup for the work. And the unit will be joules or Newton meter. Let's see another example.